This year my entry in Sum 3 will be a document. It's not done yet, but let's see what I have so far. How to divide by zero, and other things you will learn in high school calculus. This will give you a brief overview of calculus. This will not replace your calculus textbook. This will help you understand what you are learning in class and why. When I first learned calculus, we focused on the mechanics of solving problems. I wish we'd spent more time discussing why we were learning these things and what they meant. Intended audience: someone who is about to start high school calculus. Someone who studied calculus in high school but doesn't know why. Someone who enjoys math and wants a different perspective. Me, back when I was first studying this subject. Jump right to where you're interested in, but I'll just read through. Might skip the integrals because I haven't spent much time on that yet. The rest is almost done. Prerequisites. You'll need to remember some algebra to understand this document. Here is a quick refresher of the relevant facts. You'll need a lot more algebra when you're ready to actually solve calculus problems. Graphs of functions. You should be familiar with graphs of functions. Graphs are the easiest way to explain and understand calculus. And you can click on one of these to go to Desmos, or some of them take you other places. The dark horizontal line is called the x-axis. The numbers along the line are the inputs to the function. These are often things you can change. The dark vertical line is the y-axis. The numbers along this line are the outputs from the function. If you give your computer or calculator an input to a function, it can compute the output of that function. Sometimes we write f of x and say f of x instead of y. Slope of a line. Slope is defined as rise over run. In the graph above, you can see the function moves 2 units up every time it moves 3 units to the right. So the slope is 2 divided by 3, or 2/3. You could also say that the function moves 4 units up every time it moves 6 units to the right. And it moves 6 units up every time it moves 9 units to the right. 2 divided by 3, 4 divided by 6, and 6 divided by 9 all give you the same answer, 2/3. In the next graph, notice that g equals 2x divided by 3 plus 1 has a different slope, has different values than f of x equals 2x divided by 3, but they both have the same slope. Obviously, you could jump past parts that you already understand. This is just the prerequisites. The next graph shows a line going down, so it has a negative slope. You can see that the function moves 2 units down every time it moves 3 units to the right. So the slope is -2 divided by 3, or -2/3. I like the way these pictures came out. I started with Desmos. And I used a screenshot, there we are, from Desmos, and that's what you get if you click on it. But I didn't like their annotations, so I added my own annotations in SVG, and later you'll see some of them are even animated. Does really high quality work. It's as you zoom in, it really looks good. So the SVG, I'm still learning that tech, but it really works well for me. Back to the document. Horizontal line has a slope of 0. In this case, the rise will always be 0. The run can be any number I choose. Let's say 42. 0 divided by 42 equals 0, so the slope is 0. If the line is vertical, its slope is undefined. In this case, the run is always 0, and anything divided by 0 is undefined. Or is it? Keep reading. Limits. Limits are a way to divide by 0 and otherwise make infinity work for you. In calculus class, you will learn a more precise definition of limits and a lot of rules to help you compute them. You might have to use limits directly to solve some problems. Mostly you'll learn about limits so you can understand the definitions of derivatives and integrals described below. So you can understand the definitions of integrals and derivatives described below. Calculus focuses on smooth functions. There is a formal definition of smoothness, but your intuition is right. Let's look at some examples. 2 minus x squared is smooth everywhere. The absolute value of x is smooth everywhere except at x equals 0. N factorial is not continuous, so it can't be smooth. If you zoom into a smooth function enough, it will eventually look like a straight line. That makes the function easy to predict. So this one's interactive. I can click where I want to zoom in, but if I wait long enough, it'll just do something on its own. It'll give up on me and just, well, you can just stare at it if you want, but there's better images if you just want to stare. And a few notes. This needs a little bit more work. These yellow notes are just for me. They won't show up in the final document. Smoothness is the opposite of a fractal. If a function looks like the Mandelbrot set, you probably can't apply calculus to that function. No matter how much you zoom into the Mandelbrot set, you'll always find places where it is not smooth. And I don't have a list of everything at the bottom, all my a bibliography. I don't have a bibliography. You just click on an image and you see where it came from. Same thing here. This will take you to a nice article. I'm not getting into fractals. Fractals are the opposite of what I'm discussing here. Read that again. Smoothness is the opposite of a fractal. If a function looks like the Mandelbrot set, you probably can't apply calculus to that function. No matter how much you zoom into the Mandelbrot set, you'll always find places where it is not smooth. The same goes for natural fractals, like the coastline of Britain. No matter how much you zoom into a natural coastline, you will always find more details. It will never look like a straight line. It will never be smooth. Filling in missing values. Let's look at the function f of x equals x to the third divided by x squared. Naively, you might simplify that to x squared. That's almost right, but remember that you are not allowed to divide by 0. So you should really say x to the third divided by x equals x squared, but only when x does not equal 0. X to the third divided by x is undefined when x equals 0. Notice the open circle at x equals 0. This was one of the biggest problems I had with Desmos. I didn't like the way it drew that, and this is an important part of the paper, so that's why I started using more SVG to update these pictures. In simpler terms, x to the third divided by x looks a lot like x squared, but x to the third divided by x has a hole in it. If you only had the first graph, you could probably guess what the second graph looked like. You could fill in that hole with anything you want, but only one value would make the function smooth. Congratulations, you just computed a limit. Calculus class will teach you when it's okay to use the complete version of the function rather than the original version with the hole. Terminology. If you see delta and epsilon in a problem, it is probably talking about limits. These are written with lowercase Greek letters, delta and epsilon. Again, you can go somewhere else if you want to see the formal definition. I'm very high level. I'm not going to get into the definition. The formal definition, that is. Derivatives. Definition. A derivative is a rate of change. For example, let's say f of x tells us the total number of cookies in your house at a given time. Then the derivative of f of x tells us how quickly you are eating these cookies or baking new ones. The graph above shows that the total number of cookies goes down over time. That means that someone is eating your cookies. The graph would go up if you had baked or bought more cookies. Also notice that f of x is continuous and smooth. That means that someone is eating a little bit of a cookie at a time, continuously. Alternatively, what if whole cookies were disappearing at once? Then the graph might look like this. This function is not smooth everywhere. We can only talk about the derivative where it is smooth. Where it is not smooth, we say the derivative is not defined. Derivative of a line. Our cookie example is a straight line. The derivative of a line is the slope of the line. In this case, someone is eating 1 cookie per minute. The rate of change is -1 cookies per minute. Smaller pieces. The following example is a little more complicated. You could say that the average rate of change for the first 5 minutes is 1, just like in the previous graph. That's correct, but it's leaving out a lot of details. Let's examine the graph in pieces. For the first minute, the graph has a slope of -2, so the derivative in that section is -2. For the next minute, the graph has a slope of 2, so the derivative in that section is 2. For the next 2 minutes, the graph has a slope of -2 again, so the derivative in that section is also -2. This fifth section, the graph has a slope of 0. Need to fix that. So the derivative is 0. The following graph shows the derivative of the previous graph. Notice that the derivative is only defined where the original function is defined, continuous, and smooth. Really small pieces. That last example was a little too contrived. Let's go back to a parabola. What's the derivative of x squared divided by 2? I'll start by drawing some line segments to create a simple approximation of this parabola. I'll draw 1 point at each integer value of x. You know how to take the derivative of a series of line segments. Just like in the previous section, you need to plot the slope of each line segment and draw an empty circle anywhere the slope changes suddenly. That will give you a graph like this for the derivative of x squared divided by 2. So a lot of these links back because the whole idea is that math builds on itself. So previous section was this simpler example. And you can break the parabola up any way you want. What if you asked for twice as many line segments? Then the answers would look like the next two graphs. Is it reasonable to approximate a parabola with a lot of line segments? Yes. Remember what you saw in the zooming in demo above. Zooming in demo. As we zoom in, any one part of a smooth function will look more and more like a straight line. As you look at smaller and smaller sections, you see more and more detail. How small can we make these sections? As the line segments get smaller and smaller, our results get even more and more precise. What if we asked about a change of exactly 0? Every time x moves 0 units to the right, x squared moves 0 units up. And 0 divided by 0 equals what? The orange line above shows the actual derivative of the function, and the blue lines show our approximation of the derivative. No surprise. Our approximations were getting closer and closer to the right answer. Also notice that we have more open circles, unknown values, as the approximation gets more precise. Can we really jump from an infinite number of open circles to a solid line? Yes. That may look intimidating now, but by the time you get to this, you will already be a master of limits. When you work out the problem in class, you'll eventually learn that the derivative of x squared divided by 2 is x, matching the graph. Along the way to x, you'll see something like 0 divided by 0 plus x plus 0. Because you know limits, and because you'll know limits, you can simplify that into x without being afraid to divide by 0. Physics examples. This first example highlights the position, velocity, and acceleration of a pendulum. As you can see, they are clearly related. Velocity is the derivative of position. The position of the pendulum is changing fastest when the pendulum is in the middle, so the velocity arrow is biggest at that time. The velocity arrow points in the direction that the pendulum is moving. The velocity arrow disappears and the velocity becomes 0 each time the pendulum changes direction. Acceleration is the derivative of velocity. Notice how the acceleration arrow acts similar to the velocity arrow, but the acceleration arrow is slightly in the lead. Also notice how the velocity arrow is similar to the position arrow, but the velocity arrow is slightly in the lead. Need a little imagination for this one. As the graph above shows, all three functions are actually sine waves. The difference is that they are offset from one another. In proper terminology, they are out of phase from one another. Probably add arrows very similar to the last example to this one. A mass on a spring acts very similar to a pendulum. Once again, we use a sine wave as a good approximation of the position of the mass. So the math will be the same. A mass on a spring problem is just a pendulum problem in disguise. Pay attention when your teacher explains the calculus of sine waves. They are important and they come up a lot in physics and calculus. Here's one example. Here's one more example. And this hasn't been animated yet, but electron going back and forth in that circuit. In this case, you're watching an electron bouncing around a circuit. But the math is the same. We talk about charge instead of position. And the derivative of charge is current instead of velocity. Charge, current, and the derivative of current will all be sine waves, as in the previous example. I should remind you that these are simple approximations. This is as far as you will get in high school calculus. If you want to learn about friction and resistance, you'll need to wait for differential equations class. Till then, you live in a safe and magical world with perpetual motion. Oh, this will take you back to Wikipedia. And these were all me. That's just SVG and TypeScript. Interest rates. Interest is the money the bank puts into your bank account. Your balance will change over time because the bank is adding money. If f of x represents the bank balance, then the derivative of f of x says how quickly the bank is adding money. Bankers often quote rates in different ways. They might quote a rate for a year, but they add money more than once a year, and the rate constantly changes. Sometimes they talk about interest compounding yearly, quarterly, monthly, daily, or continuously. APR is banker speak for continuously. That's the same approximation that we did above. The smaller and smaller time span you look at, the closer you will get to the ideal or continuous value. So that was the really small pieces example, where we showed how you could step through and get smaller and smaller until eventually you approach the line. There are more details. I'll leave those to your teacher. Pay particular attention when you get to e to the x. Terminology. The derivative of f of x is often written as f prime x, pronounced f prime of x. The derivative of y is often written as dy/dx, pronounced the derivative of y with respect to x. It can also be written as y prime. You may hear the term tangent line. A tangent line is a slight variation on what I discussed in really small pieces above. Start from any one of those really small line segments. Extend it forever in both directions so it's easy to see the slope of that line segment. The graph below shows multiple tangent lines. Notice how each tangent line touches the parabola at exactly one point. That point is where the original tiny line segment is. The derivative at any point on a curve is the slope of the tangent line at that point. Let's try zooming into this example. So again, we have an image that was just copied. That's just the original graph before I added any animation. And here we have the actual line. It's not really infinite. I just approximated it because I knew how far it would go and the group that it's in. And this is all the program does. It fills in different values for the position and the rotation. And I stole this code from the interactive example, which is really the same thing, where the arrow had to rotate, so it always pointed exactly tangent to the, or exactly normal. This one's going the same direction, that's tangent. The arrow is perpendicular or normal. So yeah, all I'm doing is writing these strings, which I could do by hand, but the computer's just constantly updating that automatically. The integral section, it's probably pretty close, but until I start adding actual pictures, it's hard to say. Another animation here. I wanted to show off any number. Need some images here. Final thoughts. That was a quick tour through a full year's worth of calculus. There's no need to memorize anything. but keep this handy while you study calculus. Enjoy your studies. I'm just scratching the surface of what you will learn in class. I am Philip Smolin, writing this for the Summer of Math Exposition 3 contest, Sum 3. Click on the images or attribution for other details. Too long didn't read. Calculus is the study of smooth functions. Limits are about filling in missing values. Limits are about making infinities disappear. A derivative is a slope or a rate of change. Pay particular attention when you get to e to the x and sine of x. An integral is the area under the curve. Don't forget to write plus c. Thanks for taking the tour with me.